couple of questions we want to answer about climate change. What's causing climate change? Do we understand all the physics that are associated with those changes? Have we taken into account all the greenhouse gases? And what role do clouds in climate and aerosols and all these other things play in climate change? And that includes hurricanes and how hurricanes might change as a function of climate. So we got a picture here. This is the kind of a picture of the greenhouse effect. It's a cartoon, but really it's a picture of how energy works on our planet. Of course, all the energy on our planet comes from the sun, and that energy comes in. It comes through the atmosphere and then hits the Earth. The Earth is then warmed up by the energy from the sun and then emits its own energy, which we call infrared radiation. So the Earth emits infrared, and the sun emits visible radiation. Some of that energy makes it back out to space from the Earth, and then some of it is trapped by the atmosphere, and that warms the planet. And so that's the greenhouse effect. Ozone, okay, way up high, about 30,000 feet up in the atmosphere. If you guys have ever flown in a jet aircraft, just flying around the country, you're flying in the ozone layer. You look out the window, that's the ozone layer you're actually flying through, okay? Ozone, like we said, does absorb a little bit of infrared radiation, so it acts like a greenhouse gas. It also is very good at absorbing ultraviolet radiation from the sun, okay? That ultraviolet radiation, if it weren't for the ozone layer, would come down and hit us, hit plants, hit all the people and animals, and cause all kinds of problems. It's a very strong form of radiation that can break apart the nucleuses in our cells and cause cancer and all kinds of diseases. So the idea is we want to, we're lucky in that we have evolved that the atmosphere blocks that ultraviolet radiation for us, and it does that by breaking apart the ozone molecule. So again, ozone absorbs and emits infrared radiation, absorbs ultraviolet radiation, and protects us from the sun. And so that's another topic that we care about. And the way we study that is by using satellites that measures energy. Remember, everything comes down to, can we measure the amount of energy, either sunlight or Earth-emitted infrared radiation? And if we can measure that radiation, we can understand all those things that are happening in the atmosphere. And so some of the examples we'll talk about are some of these hurricanes. And the way we do that is using a whole bunch of different satellites. And this is a picture of the A-Train. I noticed that one of the users here has an A-Train username. And that's what this is. This is a picture of, right now there's 5 satellites, and eventually there will be 7 satellites on orbit that all follow along each other like cars on a train, and we call it the A-Train. The mission I work on is called CloudSat, and that's it's the 4th satellite from the right. And CloudSat is a satellite that's designed to measure the properties of clouds in the atmosphere. And we'll talk a little bit more about what that data looks like in a couple of slides. But the idea is that all of these satellites measure some different part of the radiation from either the Earth or from the sun. And that's radiation that's come down off the Earth and is coming back up towards these satellites. And by measuring that radiation and the 3 things that radiation can do, which is being emitted, absorbed, or scattered, we can actually tell a lot about the physics of the environment. So how does that relate to hurricanes? We have a picture here of something called El Nino, and you guys probably know a little bit about El Nino and how it's measurements of ocean temperature and how sometimes it gets warmer or sometimes it gets colder in the Pacific. How we actually measure that? How would you measure the temperature of an entire ocean? You'd need a lot of thermometers if you're trying to do it directly, and it would be really hard because you'd have a huge area to try and cover. So what we can do is we can measure the emission of energy from the ocean. Remember that the amount of energy emitted is a function of the temperature. So if it's warmer, it changes the radiation. So if you measure that radiation, you can actually tell what the temperature of the ocean is. And so that's one of the things we can do. And so the picture here, there's 2 kind of pictures of the ocean temperature, and the top one is kind of a normal season. And if you look here off the coast of South America and near the equator, you can see there's kind of a yellow band right by the equator, and that's kind of cooler temperatures. Red means warmer. So in a normal year, it's fairly cool here right along the equator in the ocean. On an El Nino year, if you look at the bottom picture, you can see instead of a yellow stripe along the equator, it's actually all red, so it's a lot warmer there. Okay, so that's something we can measure from satellites. Now you may be thinking, well, big deal. Who cares if the temperature's warmer? Well, what happens is when you have warm water, that creates thunderstorms. Oh, no, sorry. This is what's called an anomaly plot, where you can actually see that the change, and you can see during a normal year. This is just kind of average, changes. During an El Nino year, this red stripe tells you where it's gotten a lot warmer in the ocean. So this is where the difference is in the Pacific Ocean. Why that matters is, anytime you have a thunderstorm being created, that's the air in that thunderstorm goes up to the top of the atmosphere, and then it has to go somewhere. So at the top of the atmosphere, it spreads out and makes these little cells. And I wish I had a laser pointer to show how this works, but you can imagine air going up through the thunderstorm here over South America, going up to the top of the atmosphere, and then it spreads out and then goes down on either side of it and then causes sinking motion. So here, if you look off the coast of South America, there's sinking air over here over the Pacific, and then there's sinking air over here over the Caribbean, okay? So if you shift where the warm water is on the planet, you shift where this convection occurs, where these thunderstorms occur, and you shift where the sinking motion happens, okay? This goes all the way across the planet. You can see there's a couple of spots here over South America, here over Australia, and here over Africa, where most of the thunderstorms happen. If you shift where the warm water is, you shift where those thunderstorms happen, and you move the sinking air. What that means for hurricanes, sitting here in Florida, those hurricanes are coming in over the Caribbean. If you shift the temperatures in the Pacific Ocean, you might actually shift that sinking air right here over the Caribbean. So if a hurricane forms in the Atlantic and comes towards Florida, it runs into an area of sinking air, and that might actually tear the hurricane apart. 2005, if you guys remember, was a huge hurricane season. Hurricane Katrina happened that season, and they had so many hurricanes that they actually ran out of names, and they had to start going with Greek letters just to name all the hurricanes they had. 2006 came along, and they had nearly the same conditions, and everyone was worried that it was going to be another epic hurricane year. But what happened in 2006 was there was an El Nino that shifted this convection that we talk about, and there was a lot more convection in the eastern Pacific, and that put a whole lot of sinking air over the Gulf of Mexico and over the Caribbean, which killed the hurricanes. And so there were very few hurricanes in 2006, even though the conditions were better for hurricanes in 2006 and in 2005. Because of this sinking air, we actually didn't get as many hurricanes as we otherwise would have, okay? And that's something that we can actually study by using satellites and by measuring the emission temperature of oceans and seeing where the oceans are warmer. All of a sudden, now we can make better hurricane forecasts and understand where hurricanes are coming from. So if we want to observe the structure of hurricanes, that's where we use satellites like CloudSat. I'll give you a brief example of how CloudSat works. CloudSat is kind of like a big microwave oven in the sky that's emitting microwave radiation. It's almost the same frequency as what you have in a microwave oven, and you choose that frequency because microwave energy likes to interact with water droplets, okay? In your microwave oven, if you put a lot of microwave energy in there, it excites the water, and the water vibrates and moves around, and the friction caused by that is what heats your food up, okay? Our satellite isn't quite that strong, but it does send down some microwave energy, which bounces off of cloud droplets inside the clouds, and then it measures how much energy comes back to the satellite. So it sends out a pulse of this energy, and then it listens to see what comes back. The more water there is in the atmosphere, the more signal comes back, and that tells us how much water there is in the atmosphere. So what we have here is a picture of a hurricane, and I have to zoom in here a little bit to make sure I can see all the details. This is Hurricane, I believe, Bill from a couple years back, and up here on the top left is kind of a standard satellite picture from a regular satellite that's up in space taking a picture of the top of the hurricane. There's a red line, if you guys can see it, going right over the eye. That's the track of our satellite called CloudSat, and that's where CloudSat flew over the satellite. If you look underneath the picture of the white hurricane, you can see this kind of blotch of colors. What that is, along the bottom of that blotch, that's the surface, and then the top of it is the top of the atmosphere. Okay, the colors inside that's the actual amount of water inside the hurricane. So you can think of the bottom blotchy bit as an X-ray that looks inside a hurricane and sees what the structure is. And you can see, coming from the right to the left, you can see lots and lots of this red coloring, and that's where it's raining really hard. And then there's little breaks where it goes from red to yellow to red to yellow to red. Where the yellow is, that's the bands of the hurricane. So you're seeing strong rain and then not much rain, more strong rain, not much rain, and then a lot of strong rain going all the way up to the eye. And you can see this white kind of area right in the middle here. That's the eye of the hurricane where there aren't any clouds. And then you come to the other side of the hurricane, you can see strong rain, and then a band, and then another band of strong rain, and then weakening out all the way to the edge of the hurricane. We never were able to see this kind of structure with hurricanes before. If you put a radar on the ground and get it close enough to a hurricane, you'll get a couple of observations, but then what happens is the hurricane destroys the radar and you don't see anything else at all. So this is the first time we were able to see inside hurricanes, and the information we're getting from this data we're actually putting in our hurricane forecast models to make our understanding of how hurricanes work better, and then that gives us more accurate forecasts for hurricanes.